In our last two lectures, we discussed about the single phase inverters and the three phase inverters. And in both the lectures, we discussed about the operation of the bridge inverters to convert a DC supply into either a single phase output or a three phase output. So we basically discussed the scheme, but we did not discuss anything about the voltage control. However, when the load is to be supplied, the load demands a variable voltage. Now, how we could vary the voltage? That is to be understood. In this lecture, the discussion shall be on the control of the voltage that we are getting through an inverter. Now, this control, how we can give a variable voltage to the load, this is to be understood. Now, there are three ways by which we can control the voltage of an inverter. The very first way is, let us say this is the inverter. This red box, let us say this represents an inverter. Now, this is the output voltage, this is the input voltage. Now, there are three steps. One, this output voltage. Second, this inverter itself. And third, this input side itself. So there are three steps. At any step, you can control the voltage. Like you can control the voltage here. Here means inverter has given a voltage. Now you control it. You use whatever thing you want. You control the voltage once it is received from the inverter. This kind of control is called external control of AC output voltage. Means the AC output is available and now you are controlling it externally by using an external device. This is one step where you can control the voltage. Similar way, you can control the voltage at the input side as well. So this makes the second type of method control, second type of voltage control. Instead of controlling the voltage at the output side, you control the voltage which you are feeding at the input side. So this becomes the external control of DC input voltage. Means you control the input voltage externally by something. And third is, if you don't want the voltage to be controlled here, if you don't want the voltage to be controlled here, then you can have a control which is applied in the inverter itself, which controls the voltage, and there is some scheme which gives you the variable voltage here itself. So third control becomes the internal control of the inverter, where you are focusing on the control which is applied inside an inverter and you are not using any external device for the voltage control. So there are three methods. So let's start with the first method, that is the external control of AC output voltage. Then we will discuss this second method, and then we will come to this third method of internal voltage control. Now let's start with the first method, external control of AC output voltage. External control means inverter has given the voltage here. You apply whatever control you want, you apply after this point. Now, after this point, there can be two methods. One is you can use AC voltage controller, or you can use, second is you can use series inverter control. Now, what is it? Here, you got the voltage. After this, you apply, you connect an AC voltage controller. This voltage controller will convert this voltage into the control output and it will be fed to the load. So it will be a two-step conversion. DC into AC, then AC is controlled by AC voltage controller, then finally it is fed to the load. So this is the one way. Second way is series inverter control. In series inverter control, what you do is you use two inverters. Now the input is given to these inverters. To this one inverter, there is a transformer connected, and to second inverter, there is another transformer connected. There can even be more inverters, so more steps can be added. Now this transformer has a separate primary, this transformer has a separate primary, while the secondary of these two transformers is connected. Now, the voltage available at the secondary of upper transformer is V01 and at the lower transformer is V02. These two are in different phases. So these two, by the phase control of these two, you can control the voltage V0. So V0 will be a summation of these two voltages and it will be V0. So by varying this angle theta, you can control the output voltage. So this is called series inverter control. These two control, both of these controls requires additional devices. And when you are using additional devices, you are investing more. So the scheme becomes expensive. You are giving a space for the more losses, because now the losses will also happen in AC voltage control, or if you're using series inverter, then this will have losses. So you are somewhere reducing the efficiency as well. So you are, by adding more stages, you're making the system bulky, complex, then you are making it expensive, and on the other side you are also increasing its losses and reducing its efficiency. Similar type of control, similar type of control, like here you are controlling the AC output. Similar type of control is you control externally the DC input. So when you control the DC input, the DC input, this is the input which is given to the inverter. So here the last step is inverter. But before this inverter, we have added few stages which are controlling the DC input. So DC input can be controlled with the help of a fully controlled rectifier, the phase control rectifiers. Or if you don't want to use a control rectifier, if you're using an uncontrolled rectifier, then you can have a chopper with it. So here chopper will provide the control over DC. Here fully controlled rectifier will provide the control. Or you can have an AC voltage controller. You feed the system by constant AC. You convert it into variable AC, then convert it into DC, and finally you get the controlled AC. So here one more step is added. Or you can directly, if you have the DC supply available, then you can directly use chopper. So basically in all these four schemes there is one controlled device. Like here the control device is this. Here it is chopper. Here is it AC voltage controller. Here it is chopper. At every step you are using a filter as well. You are using a filter as well. So also this method is also not very much used, because it also includes more power handling stages, which results in more losses, reduced efficiency. It increases the weight, size, cost, and complexity. The filter circuit also reduces the efficiency and makes the transient response sluggish. So here these are the few of the problems. These problems are associated with both of these controls, which is applied to the external AC, which is applied to the AC output or to the DC input. So these two are the waste methods. These are not used. Now, what do we do actually? How do we control the output voltage? Output voltage is controlled by the internal control of the inverter. Now, what is this internal control? In internal control, we kind of vary the width of the voltage that we are receiving through an inverter. Just try to recall. Let me draw the waveform of a single phase inverter. A single phase inverter gives you something this type of waveform. Now in this waveform, this is the pulse width. Now by controlling this pulse width, we can control the voltage. So if this pulse is reduced, the voltage will be reduced. So by reducing this, you can reduce the voltage. So, or I can say that by controlling the width of this pulse, you can control the voltage of the inverter. Now in this method there are merits. What are those merits? First is you are not requiring any additional component. So the disadvantages connected with the external components are all gone. You don't require any additional component, so the efficiency will not be affected. System will not be bulky, system will be as it is. Cost will not be increased. The second advantage of this is lower order harmonics can be eliminated. Now, harmonics, whenever we are using a power converter or some inverter, it introduces harmonics. You might have realized, like here, as I said, the the output waveform of the output waveform of the inverter is a kind of rectangular wave. So you might have noticed, if you have an inverter in your home and that inverter is not a sinusoidal inverter, then whenever you are switching your devices, you would have noticed some humming noise which is coming out of the devices. Like if you are running a fan on an inverter and the inverter is not a sinusoidal inverter, then there will be a sound through that fan. Why that sound is why that humming sound is coming? It is because the inverter you have used does contain harmonics. If the inverter contains harmonics, it will produce the devices will produce the humming noise. Now this harmonics, more the waveform is away from the sinusoidal one, more will be the harmonics. So harmonics are there in this kind of waveform because this waveform is totally different through the sinusoidal waveform. Now these harmonics, any waveform, when you will perform its Fourier analysis, you will get to know how much harmonics is contained in this particular waveform. Yeah, how much this waveform is different from a sinusoidal waveform. That analysis can be done through the Fourier analysis. And when you go for the Fourier analysis of such output of the inverter, you find that there are a lot of harmonics. Now by this PWM technique that I'm talking about, that is, if we control the width of the pulse that we have got through inverter, by this kind of control, what we can do is we can eliminate the lower order harmonics, and higher order harmonics, they will still persist. But I think you all know that higher order harmonics can be easily filtered out. If we compare the filtration of these two harmonics, lower order harmonics are difficult to remove. However, higher order harmonics can be easily removed. So this is the second advantage that this internal control gives us. It reduces the filter requirements. Now, what is the disadvantage of this technique? If you are controlling the internal, if you are controlling the inverter internally, that means you are playing with the switching of the devices. By changing the sequence or by increasing the switching speed of the devices, you can achieve the PWM. But as I said, by increasing the switching speed, that means if you are increasing the switching speed of the devices, so you will have to use those devices which have low turn on and turn off times. So the devices having low turn on and turn off times, those devices are expensive. So the cost by this method of PWM is increased. That is the reason, maybe because students should know it. I can give you it. I can give you an example to explain this. When a student, say, if you go out to purchase an inverter, you go to the market, you ask the shopkeeper to give you an inverter which is rectangular, which is giving you the rectangular pulse. That is the non-sinusoidal inverter. The non-sinusoidal inverter will not be costly. However, if you ask him to give the sinusoidal inverter, it would be costly. Why it is costly? Because the devices which it is using, those devices are high speed devices, and that is why the control becomes little more complex, and there are few changes that you need to make inside the inverter which increases its cost. So this is the only disadvantage. However, in 100% of the cases, it is the internal control of inverter which is used. Now, how we go for it? We go for the inverter control, internal control by pulse width modulation. This is the only solution. Now, pulse width modulation can be done in three ways. The first way is the single pulse modulation. The second way is multiple pulse modulation. And the third way is sinusoidal pulse modulation. Now, these three have different way, like these three will be different in terms of the harmonics that are contained in the output voltage. So let us see how we go for it. To understand this, let's first discuss the single pulse modulation. In single pulse modulation, what we do is, this is the output pulse of the inverter. We will just play with the width of this pulse. We can reduce this width, like here in this case we have reduced this width, and let us call this width as 2d. Now this pulse 2d, this pulse of width 2d, it is, you can see, it is the positive pulse and it is symmetrical about pi by 2. A similar pulse at the negative side, you will find this is symmetrical about 3 pi. So the this is the control, like instead of switching the device here, we will switch on the device at this point, and then the device will be switched off at this point. Similar way for negative, device will be switched on here and switched off here. Now this waveform, which is chopped from both left and right side here, and here also left and right side, this kind of output waveform is called quasi square waveform. And if you wish to find out its RMS value, then the RMS output voltage will be Vs 2d by pi under root. Now this gives you the output RMS, and it can easily be realized, not a problem. Now here the output voltage will be more in this case, in case of this, because here the pulse width is equal to pi. The pulse width here is equal to pi, but here in this case the pulse width is less than pi. So as long as you are like, if you are reducing the width, if you are reducing this width, the output voltage will be reduced. That is why it is written that output RMS voltage has a direct relation with D. More is the value of D, more is the value of output. Now let's consider D as equal to pi. If D is equal to pi, what will happen? If D is equal to pi, it is 2 pi upon pi, or you can say it is equal to Vs root 2. Now Vs root 2 will be the value of V naught R. Vs root 2 will be the value of, sorry, 2d upon pi. 2d, if we keep this 2d as, if we keep this 2d as pi, so it will be pi upon pi, it is 1. So output RMS voltage will be equal to Vs. So it will be the same as the input voltage, because here sometimes student also makes this mistake. Instead of considering it 2d, they consider it d, as I considered. It is not d, it is 2d. So if this 2d is equal to pi, the output RMS value will be equal to Vs. Now by controlling this 2d, we can control the output voltage, and this 2d may vary from 0 to pi. The minimum value can be 0 and the maximum value can be pi. Now if we make the Fourier analysis of this quasi waveform, if you make the Fourier analysis, you will find that the coefficient an is 0. Why coefficient an is 0? Because the waveform is symmetrical. And if you solve it for bn, you get this value. Now here it could be seen. Now if you further solve this series, you get the output voltage as summation of this for n equals to 135 up to infinity. Now 1 stands for the fundamental component of the voltage. Now here the point to be noticed is that this voltage, this output voltage, has a dependency on D. And in fact, the third harmonic has a dependency on D. The fifth harmonic has a dependency on D. So basically, the fundamental component, whatever voltage it is, whether it is the fundamental component or the harmonic component, it will have the dependency on D. Now, let us see what is the effect of this D on various harmonics and on the fundamental component. Now, when the pulse, this is the case 1, you can say, when the pulse width is 2D and this 2D is equal to pi. If the pulse width 2D is made equal to pi, then the fundamental component of voltage will become equal to 4 Vs by pi. This will be the fundamental component of the output voltage, and it will have a peak value of 4 Vs by pi. Why? Because for 2D, for for 2D equals to for 2D equals to pi and n equals to 1. Here we have taken n equals to 1 and 2D equals to pi. For this value 1, and if 2D is pi, D is pi by 2. So sine 90, and this is also sine 90. So sine 90 is 1. So this gives you the value of output voltage as 4 Vs by pi. Similar way, if you wish to find out the peak value of the nth harmonic, then simply write the value of n here. For third harmonic, it will be like 4 Vs upon 3 pi sine 3d. For fifth harmonic, n will be 5, and so on. So if we divide, let us call this as equation number 3. So equation number 3 gives you the peak value of nth harmonic, while equation number 2 gives you the peak value of the fundamental component. So if you divide these two, we get VO Nm by VO 1m as sin Nd upon n. Now this ratio of harmonic voltage to the fundamental voltage, this is drawn here. Now this is drawn here. Now this is the value of n equals to 1. Now n equals to 1. Now this value is 1. This 1 means VO Nm upon VO 1m. That means this value is 1. If this value is 1 means sine D equals to 1. If n equals to 1, sine D equals to V1m by 1. This is 1. So n is equal to 1. This gives you the plot for sine D. N equals to 3. It gives you the plot for, if I make this as 3, it will give you the plot of sine 3D upon 3. So it gives you the plot of sine 3D upon 3. And similar way, this is plotted here. Now let us see, because by this I would like to give an analysis. Let us say that the fundamental component for this quasi waveform, let us say this width 2D is kept as 60 degree. If I keep 2D as 60 degree, that means D is 30 degree. If D is 30 degree, that means sine D sine D will be sine 30 degree. Sine 30 degree will be, that means it will be 0.5. So the fundamental component will be reduced to 0.5. And if for the same value of 2D equals to 60 degree or D equals to 30 degree, if I wish to find out the amplitude of third harmonic, it will be 1 by 3 sine 90. It will give you 0.33. That means by keeping the value of D equals to 30 degree or 2D equals to 60 degree, we have got a fundamental component of 0.5, whereas we have got the third harmonic as 0.33. The difference between these two is of 1/3. Like this harmonic component is 2/3 of the fundamental component. Now if you consider even lesser value of 2D, if you consider a value less than 60 degree, if you consider it 30 degree or say 20 degree, then the fundamental component will be further reduced. If you reduce the fundamental component, what you will realize what you will realize is that the fundamental component is reduced. However, the harmonics 3, 5, 7, they are not very much reduced. Like here, this difference is of 1/3. But if you go on reducing the voltage, you will find that the harmonic voltages and the fundamental voltages are more or less same. Like for this case, the harmonics voltage should be around 0.11 or 0.12 or something. So there won't be much difference between the fundamental component and the harmonic components. That means if you reduce the voltage by this method, it introduces a great deal of harmonics. If the voltage is reduced, the fundamental component is the one which is reducing, but the harmonic contents are not very much affected. So in this method, in this first method of control, which is this method, single pulse modulation. In this particular method of modulation, we are not getting a good control over the harmonics. So there is one more method which we can try. There's another method which we can try. That method is multiple pulse modulation. Now, what is this multiple pulse modulation? Instead of bringing one pulse at the output, we will we will switch on the devices in such a way that we get a positive pulse, then again a positive pulse, then a gap, then a negative pulse, and then a negative pulse. So basically, in one half, we have got two pulses. We can get three pulses, four pulses, five pulses, six pulses, depending upon the what exactly you want at the output. Just for the understanding, we have considered two pulses at the output side. Now let us say one pulse is of width d. So if this pulse is d, the another is also d, and this would also be a symmetrical waveform. Now if it is d, both of these joined together will make 2d. This could be compared with the voltage output of the first method. This quasi-square wave, it is of the width 2d, and here also if we consider this as d, this is also 2d. So basically in both the cases, the output RMS voltage will be same. So this is the same formula that I had written for the quasi-wave waveform. Now here, by splitting this pulse into two, let us see what happens. If we split this into two, what effect does it give on the harmonics? Here, when we split and make the Fourier analysis, we get the coefficient Bn as the one written here. Here, this 2 is taken because there are two pulses. Now, when we solve it, in this Bn, we see that this coefficient is dependent upon two values. One is this gamma and another is d. So here it is the output voltage. If you further solve it, you will find that the output voltage is not only dependent upon D, it has now got dependent upon the value of gamma as well. Now what is gamma? This is this value. This is called gamma. The angle between 0 and the mid of the first pulse. Now this is gamma. Now let us see how we could find it. There's a simple formula for it. It is given here. Gamma is given by pi minus 2d n plus 1 plus d by n. This could be easily derived from this figure. I would like the students to derive this formula. Now here, the value of gamma can be find out this with this formula. Let us say if we compare this multiple pulse modulation with the single pulse modulation, let us see which is better. If we compare, here we have made its Fourier analysis. By Fourier analysis, we have got this as the voltage equation. And if we wish to find out the amplitude of the nth harmonic, then the nth harmonic will be given by Vn 8 Vs upon n pi sine n gamma and this. Now here if you wish to eliminate this particular voltage, let us say it is the third harmonic. If you wish to eliminate this third harmonic, then what you could do is you make the value of gamma, equals to pi by n. You make this value of gamma equals to pi by n. If n is 3, pi by 3, 3 will cancel out, this will become sin pi, and sin pi is 0. It will make this harmonic voltage as 0. Similar way, if you make the value of d equals to 2 pi by n, 2 pi by n means if you write here as 2 pi by n, this will become sin pi, and psi pi means this voltage will become 0. The amplitude of nth harmonic is given by this formula, and in this formula, by just adding the value of gamma equals to this, or by keeping the value of d equals to this, the particular nth harmonic can be excluded. Now let us see what is the harmonic, what is the fundamental component, yeah, what output we will get if we take the value of 2d equals to 72 degree. This is just a simple, this value 72 degree is taken for the simplification purpose, otherwise it can be calculated for any value. So as an example, we have taken this 2d equals to 72%, 72 degree. If we keep this value as 72 degree and we find out the output voltage in case of single pulse modulation, we get the output voltage as 0.7484 Vs. Just recall this formula, 4 Vs by pi sine d. Now if 2d is 72, d is 36, 72 by 2. So the peak value of the fundamental component of the voltage will be this 0.7484 Vs. Now for the same 2d of 72 degree, if we wish to find out the peak value of the fundamental voltage component, then it comes out to be 8. This is the formula. This is the formula. Here, if we keep the value of n as 1, we'll get the value of the fundamental component. If we keep this n as 3, we'll get the value of the third harmonic. If we keep this n as 5, we'll get it for the fifth harmonic, and so on. So we are keeping it at 1. So if it is 1, 8 Vs upon pi sine 1 into gamma. Now gamma we have calculated using this formula. Gamma has come out to be 54 degree in this case. For calculation of gamma, we need to have the value of d. D is already known to us. D is 36. So if we calculate and keep the value of gamma as 54, then this becomes, this is d by 2, this becomes 0.637. Now if you compare this voltage with the single pulse modulated voltage, you will find that single pulse modulated voltage is more. Single pulse modulated voltage has a better magnitude compared to this voltage. So basically, by going for the multiple pulse modulation, the output voltage is reduced. By this analysis, we can say that the fundamental component of the output voltage is lower for a two pulse modulation compared to the single pulse modulation. But if you further go and analyze this method, you will find that by having more number of pulses per cycle, like here we have taken 2 pulses per half cycle, if you increase these pulses to 4, 6, 8 or even more, what you will find is that the harmonics are reduced. But which harmonics are reduced? The lower harmonics. So you will find that the lower order harmonics are reduced, but the higher order harmonics are increased. So by increasing the number of pulses at the output side, number of higher order harmonics are increased. But this is not a disadvantage, because as I said, it is difficult to remove the lower order harmonics. However, higher order harmonics can be easily removed. So by just adding a filter, we can remove the higher order harmonics. So in this method, if we compare it with the single pulse modulation, the output voltage is reduced a bit, but yes, the harmonics can easily be filtered out. Now, how do we get the modulated waveform? How do we get these pulses? To get this kind of pulsed voltage, what we do is we take a comparator. In a comparator, we we input two types of pulses, two types of waves. One is a triangular wave and another is a square wave. These two waveforms, they are compared in a comparator. Now these are the two waveforms. This is the rectangular waveform. This is called the reference wave. Here we have called it a square wave. This is referred to as the reference signal VR. It is having a frequency of omega, or you can say f. Here this total time is t, and t is equal to 1 by f. So this f is the frequency of the reference wave. However, the triangular wave is called the carrier wave. This triangular wave is the carrier wave, and it has a frequency of omega c, or you can say fc. So its time period will be 1 upon fc. However, for the reference wave, the time period will be 1 by f. So f is the frequency of the reference wave. However, for the carrier wave, the frequency is fc. Now the output, what is the output of this comparator? If these two waves are compared, you will find that there is an intersection point. Now this is a point where the voltage VC and the voltage VR is same. If the VR When the voltage VR, it tends to be, when this voltage VC tends to be more than this voltage VR, immediately the comparator output becomes high. It gives a pulse, it gives a high signal to trigger pulse generator, and this pulse generator, it generates a triggering pulse which turns on the SCR, and immediately the voltage Vs, it starts appearing at the output. Now again, the at the second intersection point, when Vc tends to become lower than Vr, it is the second output which is given by the comparator. At this time the comparator output is low. It sends another pulse, and at this time it is not the triggering pulse, rather it is the time when this thyristor is commutated. Now here the device is commutated, and so the output becomes 0. Now again at the third intersection, this pulse is given to the thyristor. Here it is commutated, then here it is triggered, here it is commutated. So at every intersection point, we trigger and commutate the thyristor. Trigger, commutate, trigger, commutate, trigger, commutate, and so on. So by doing this, we get this multiple pulses at the output. Now here I have taken the case of 4. In case you need to have 8 pulses, then you increase the frequency of this carrier wave by double. So if this frequency is made double, then it will give you 8 pulses at the output. And if you make this carrier frequency as half, you will start getting 2 pulses at the output. Now this is how we synthesize it. Let us see the third method, and the most common, most used method, which is called sinusoidal pulse modulation. In sinusoidal pulse modulation, again we are creating multiple pulses at the output, but these multiple pulses are not of the same width. Like here in previous case, these all pulses are of the same width. Here the pulse width of every pulse is different, and you can see it is more in the central pulse. Then this pulse is reduced, the width is reduced. Here again the width is reduced because the output pulse is a function of this sinusoidal wave. So the one here we compared a triangular wave with the square wave, instead of a square wave, if we compare this triangular wave with a sinusoidal wave, we will get something this type of pulses at the output. And by getting such pulses at the output, we find that the harmonics are further reduced. The harmonics are further reduced. And by doing such by using sinusoidal pulse modulation, you can further reduce the lower order harmonics, and you can increase the amplitude of the higher order harmonics, and then you further can filter it easily. Now in this method, this carrier wave, it is a triangular wave. If this triangular wave has its peak coinciding with this zero, if the peak of the triangular wave, if it is coinciding with the zero, then you get, like in this case, you will get 5 pulses at the output. Now if you reverse this, if you make the zero of the triangular wave coinciding with zero, you will get 4 pulses. So by just changing this, you can have 4 pulses at the output. Now in the first method, how many pulses you are going to get at the output, this can be calculated by a simple formula, which is given by n equals to fc upon 2f, where fc is the frequency of the carrier wave and f is the frequency of the reference wave. So if the carrier frequency is, say, 10, if the carrier frequency is 10 and this frequency is 1, number of pulses will be 5. And this is the formula when peak of this triangular wave is coinciding with 0. However, like here we are getting 5 pulses. However, if the 0 of this triangular wave is coinciding here, then the number of pulses will be this n minus 1. So when a triangular carrier wave has its peak coincident with 0 of the reference sinusoid, then there are the pulses n given by fc by 2f per half cycle. And when it is the case like this, then we get n minus 1 pulses per half cycle. Now again, how do we achieve it? The the process is similar. Triangular wave compared with a sinusoidal wave, sent to a comparator output will be high at the point of intersection. At this point of intersection, a pulse will be given to the thyristor will turn on, output will start appearing. At this intersection point, the thyristor will be commutated, then again it will be on here, off, on, off, and so on. So this is a process by which you can see, for one half you have, like in this particular case, for one half output you have triggered the thyristor 5 times and you have commutated it 5 times. So you need to have the high speed devices in this. That is why we say that in PWM the devices are little costly. Now there is one important point, that is modulation index. What is this modulation index? It is called VR by VC. VR is the voltage of the reference wave. This is the reference wave. This sinusoidal wave, this is the reference wave. Now for this reference wave, the voltage is VR, and the amplitude of this is not voltage, rather it is the amplitude. So VR is the amplitude of the reference wave and VC is the amplitude of the carrier wave. Now VR by VC gives you the modulation index, and modulation index controls the harmonic content of the output voltage, and it also controls the magnitude of the output voltage. So the magnitude of the output voltage can be controlled directly by the modulation index, and the harmonic content is also controlled. Now Mi can never be more than unity. If you try to increase the value of Mi more than 1, that means you will be using a sinusoidal pulse something like this, and in this case there will be only 2 points of intersection. So this function will not, the output voltage will not be a function of, will not be a sinusoidal function. So you you cannot have the value of Mi more than 1 if you are using, if you wish to have the sinusoidal pulse modulation, or if you wish to have this output wave as the function of sinusoidal wave, then the modulation index needs to be kept below 1. So if Mi is less than 1, largest harmonic amplitudes in the output voltage. Okay, there is one more point. The harmonic amplitudes in the output voltage are dependent upon the number, the number of pulses at the output side. Now, largest harmonic amplitudes in the output voltages are associated with the harmonics of the order Fc by F. Like here in this case, Fc is 10 and F is 1. So 10 upon 1 gives you 10. 10 plus minus 1 will give you 9 and 11. So by this kind of SPWM, by this kind of modulation, and by keeping Mi less than 1, what you can do is you can increase the amplitude of these harmonics Fc by F plus minus 1, and by this, by by controlling the value of Fc, you can, for any value, for any harmonic, you can select. Let us say you wish to eliminate 9 and 11, you keep the value of Fc as 10 and F as 1. So by doing this, what will happen, the harmonics of the order 9 and 11, they will become significant in the output voltage. Their amplitude will be increased. And why we are increasing the amplitude of the higher order harmonics? Because we will be easily filtering it out. So by selectively keeping this value, we can bring out, we can raise the value of any harmonics, any higher order harmonics. If you keep this Fc even more, then even more higher order harmonics can be eliminated. Now, higher value of N entails higher switching frequency of thyristors, which accounts for more switching losses and therefore an impaired inverter efficiency. Here, what is said, like if you are increasing the value of N, definitely there will be more switching of the devices. Switches will be more frequently switched on and off, and every switching action is associated with the loss. Every switching, whether it is on or off, it is associated with a loss. And if you are increasing the switching frequency, basically you are increasing the losses as well. This is the one disadvantage of increasing the value of N. However, by increasing the value of N, we are reducing the filter requirements on the other side. So this is an important point. So what we could do is, we could accordingly kind of balance, figure out, okay, what should be the value of N, so that our filtering requirements are also optimized, and the losses are also optimized. Mi greater than 1, I have already said, if Mi is greater than 1, pulse width will no longer be a sinusoidal function of the angular position of the pulse. Well, among these three methods, to conclude, among these three methods, the very first method, it gives you harmonics. In second method, it gives you higher order harmonics. It gives you higher order harmonics, which can be filtered out. In third method, by selectively keeping the value of N, we can raise the amplitude of any harmonic which you wish to filter out. So here also you can easily filter out the higher order harmonics, and lower order harmonics already they they are eliminated by this method. In in general, we go for the third method, that is called sinusoidal pulse modulation. Well, there are even advanced methods which uses selective techniques, but then since those methods are not in the syllabus, so I'm not discussing it. I think this is enough for today's lecture. These two are the reference books. Students may further go through these books to have a better understanding about inverters. Thank you.